One of the things we like to do in mathematics is to be able to solve equations. Well, it's pretty easy to solve a linear equation. And then back in the Babylonian age, there was a guy that figured out how to complete the square and figure out the quadratic formula to be able to solve any quadratic. Later in the 16th century, a couple mathematicians figured out how to solve the third and fourth degree equations and get exact answers. But because these are so complicated, we rarely use them except with computer algebra systems. To be able to solve stuff that's degree 5 or higher, there are no such formulas. So how do we go about solving these types of problems? Well, one of the ways we can do it is with Newton's method. Basically, we take a look at the equation of our tangent line, which we know you have to have a point and a slope. And so if we take a look at going f of x plus our new y value, our existing y value of our point, and our slope, which you know is your derivative, and your new x value, and your existing x value. So here's your existing ones right here we plugged in. So that would be kind of the equation of your tangent line. Looking over here on the right, and looking at the bottom one, if we have this being our first spot, we do our tangent line relatively close to where we know we're going to have a 0. And we go ahead and we find when that tangent line is equal to 0, which would be here. Well, how do you find when the tangent line is equal to 0? Well, that's when your new y value is 0. So you plug in 0 for your new y value, and then you pretty much solve it for your new x value. Well, to do that, we'd have to go ahead and take and divide by our derivative. So we would have this divided by our derivative, and that would get the parentheses by themselves, and then we'd have to get rid of this by adding it to both sides. That's what we have down here. So this allows you to be able to get to your new y value. So once you have that, you know you're relatively close, but we're going to then go ahead and repeat that process. Here's your x sub 2. We find a tangent line to our curve at that spot. And while we set that equal to 0 and we solve it, we get here. Notice on each time we're getting closer and closer to the actual value of c. And well, then we could go ahead and repeat that. Take our new x value here, do our tangent line, and we would come down and we get a spot here. So with Newton's method, you repeat this process several times. Now, a lot of times, after you do it 2, 3, maybe 4 times at the most, you have an extremely accurate answer to estimate this 0. Now, the main thing we're going to look at here is what's referred to as differentials. Once again, for the most part, we're dealing with that tangent line, where we have our point, and we have our slope, which we know is our derivative. So we take our y value of our point, equaling our slope, because that's our derivative, x minus the x value of our point. A lot of times you want to go ahead and have y on one side by itself. Well, when you have y on one side by itself, this is your linear approximation formula. So down here, that's why we have L of x instead of y, because it's a linear approximation formula. Looking at your graph over here, if you are anywhere close to A on your tangent line, then it's a pretty good approximation for that curve. You'll notice we're close to A, and if we're on our tangent line, it is really pretty close to whatever the function would be on the blue curve. It's a good approximation, and sometimes a good approximation is a lot easier to deal with than finding the actual values. Notice when you get farther away from A, your tangent line is not a good approximation. So your tangent line is only a good approximation when you are close to the value of A. So we'll go ahead and find our tangent line for this problem. We have our point. So that means a is your nice value of x. It's easy to work with, which 0 is. Then f of a then, which means a would be, once again, 0. F of a is what you get when you plug 0 into your function, which we know we get 1. And if you weren't given the point here, you could always take 0, plug it into your original function, and then you get that. Now, we also have to have our derivative. Well, it's pretty easy to do our derivative of this. We'd put the exponent in front, decrease the exponent by 1, and then we could do the chain rule if needed, but the chain rule is only 1 here, so it doesn't really make a difference. Rewriting this, taking the negative exponent down to the bottom, we would get this. So now we need to go ahead and find our derivative at the value of a. Once again, a is 0, so we need to know our derivative at 0. So if you plug 0 into your derivative, well, that gives us 1/2. Once again, a is 0. We plug in 0 here, and we get this. F of 0 was 1, and we get this. So in other words, we could simplify a little bit, and we just get 1 plus 1/2 x. So this would be a good linear approximation when you are near the point x being 0, y being 1 on your curve. Now we're going to take a look at differentials. A differential is, instead of dy over dx, just dy. Basically, it's taking your derivative and putting a dx by it. So in other words, instead of having dy over dx, once you get your derivative, you basically multiply both sides by dx. That's what a differential is. So here's your original function, here's your derivative, your differential, you multiply both sides by dx, so we would get this, and your dx would be over with the 2x. Same idea here. Here's your derivative, you multiply both sides by dx, and you get your differential. And the same idea down here. So go ahead and find your differential for these next two problems. Well, we do our derivative of y with respect to x, dy over dx, exponent down in front, decrease it by 1, exponent in front, decrease it by 1, and then we want to get dy by itself, so multiply both sides by dx. Notice it's your whole derivative multiplied by dx, so since we have more than one term, we needed to have parentheses. Over here, since we have variables times variables, we'll have to use the product rule. So we go derivative of y with respect to x, derivative of the first times the second, plus the first times the derivative of the second. Then all we have to do is go ahead and get dy by itself by multiplying both sides by dx. That's your differential.